Hello everyone. In this video we are going to discuss about design of NASA developed robotic Mars helicopter using Matlab Simulink. This example shows how to use Matlab Simscape Electrical library to model a helicopter with coaxial rotor suitable to fly on Mars. This helicopter takes inspiration from Ingenuity, the robotic helicopter developed by NASA, which accomplished by the first powered flight on another planet. These are the reference we have taken for design NASA robotic Mars helicopter using Matlab Simulink. It is in MathWorks website, and Withrow Johnson et al. Developed an advanced Mars helicopter design, and Pipenberg et al. Design and fabrication of Mars helicopter rotor, airframe and landing gear systems, and also Balaram et al. They developed Mars helicopter technology demonstrator during 2018, also published in the conference Atmospheric Flight Mechanics Conference. These are the contents we are going to discuss today. Design of NASA robotic Mars helicopter using Matlab Simulink. These are the contents. Introduction about Mars helicopter technology, Mars helicopter system level design with Matlab, and NASA robotic Mars helicopter Simulink model, and the detailed model overview of battery pack variants and various Simulink blocks, including flight control and other solar panel, and what are the remaining flight control system, command dashboard subsystem, and finally we are going to see with interactive Simscape result explorer, Matlab tool, and simulation and result analysis with graphs and all, altitude versus battery cell temperatures, and flight duration versus number of battery cell temperatures, simulation analysis, and then what are the products you need for this design, Matlab and Simscape Electrical toolbox. And introduction about Mars helicopter technology. This diagram shows the view of Mars helicopter technology. It also taken from the source Pipenberg et al. During 2019 they published paper in conference. Design and fabrication of Mars helicopter rotor, airframe and landing gear system. Based on that we developed with Matlab Simulink and Matlab Simscape Result Explorer library. The Mars helicopter is an autonomous 1.8 kg coaxial counter rotating rotor craft baseline to fly on the Mars 2020 mission to demonstrate aerial mobility on the surface of Earth. Here in this example, the rotor system, the landing gear system and the auxiliary structures and the solar array are developed. In this example, in this video we are going to implement using Matlab Simscape library. All the system, the rotor system and landing gear system and the solar array are taken with Matlab Simulink interactive library. Let us see at the time of simulation. Then the rotor system consists of the rotor blades. Here you can see the rotor system and solar array and landing gear system and electronic core modules inside this SWEB. Then there is a helicopter warm electronic box. That's this one. The rotor system consists of rotor blades, hub mechanism, propulsion motors, swash plates and linkages, and control servos, primary helicopter structures. The landing gear system includes four deployable legs, landing feet and suspension mechanisms. The auxiliary structures, including the structural elements of the helicopter warm electronic box that encloses electronic core module and battery, and the solar array substrate that serves as the structural element of the solar panel system. The solar array located above the blades is used to recharge the helicopter batteries during the day to provide power for flight operations and overnight thermal survival. And how to implement with this one with using Matlab is an introduction about Mars helicopter system, system level design with Matlab. This example includes how to use Simscape Electrical to model a helicopter with coaxial rotor suitable to fly on Mars. This helicopter takes inspiration from Ingenuity, the robotic helicopter developed by NASA, which accomplished the first powered flight on another planet. To control the helicopter attitude interactively, can use the blocks in the command dashboard subsystem. This helicopter model comprises using with Matlab, solar panel, battery pack, heater, motor and drive, two gearboxes, two contra rotating coaxial rotors, and single dimensional mechanical model of gravity, drag, mass and ground contact forces blocks can taken from the Simscape Electrical library. These are the detailed Simulink model of NASA robotic Mars helicopter. Here we can see the helicopter model comprises the solar panel, the battery pack. The battery pack, there are two types of battery packs you can simulate. One is simplified model, another one is a detailed model. Here the battery pack, and the next one is a heater and motor drive, two gearboxes, and two contra rotating coaxial rotors, as well as the mechanical model of gravity. This one gravity and drag and mass, total mass and ground contact forces. Also the scope is available for measure the attitude measurements. In this flight controller toolbox, flight controller subsystem, system level controls, and to make the simulation interactively, command dashboard functions also there. Let us see the detailed model. Here also the reusable code also there. Based on that we can modify the model parameters, we can set the battery pack variant. There are two types of variants are there, detailed variant and simplified variant. Also by using the reconfigurable code is there, so that we can plot attitude and battery cell temperatures and plot the flight duration versus number of batteries. Also by using the SSC Explorer, that is a Simscape Result Explorer, we can see the result and analyze the result, analyze the waveform with each and every subsystems. It's also very interesting. The next one, here solver configuration is there. Here in this detailed battery pack there are 6 series number of cells are replaced here. Let us see. Here the model overview of battery pack variant. This one, the battery pack variant, you can able to select the two variants. First one is a simplified variant model, and the next one is the detailed battery pack variant model. Let us see the first model. This is a simplified battery pack model. These are simplified subsystem of simplified battery pack model. This battery pack model, this block model is a battery based on tabulated characteristic as function of state of charge, so that the SOC sensor state of charge and potential temperature we are going to measure. Here also you need to modify the values called the vector of state of charge values, temperature dependent values, current directionality, vector temperatures, all the things you can based on the tabulated characteristic. This block, battery block, this block model say battery based on tabulated characteristics as function of state of charge and optional temperature. And next block, this block insulent thermal mass block. This block models internal energy storage in the thermal network. And next one, radiation to environment block. This block models heat transfer in thermal network by radiation between two surfaces. The next one, the detailed battery pack model. In this battery pack model, the battery pack contains 6 lithium ion cells connected in series, 1 2 3 4 5 6. Only the central cell is eliminated, central cell is instrumented, the central cell. And the next one, the cell transfer heat, the heater is attached to the central cell. This is a central cell. The heater is attached to the central cell. The cell transfers heat to each other and to the insulating box, which dissipates heat to Martian environment. This one. Here next control system is a flight control subsystem. In this flight control subsystem, the PID control blocks such as attitude, velocity, and rotor speed controller implements continuous or discontinuous time PID control algorithms, and also it includes advanced features such as anti-wind up, external reset, and signal tracking also possible. Once the helicopter is ready to take off, the flight control subsystem is enabled to control the attitude. It comprises these 3 PID that controls the rotor speed, the climb rate, and the altitude respectively. The output is reference torque for the motor and drive block. You can see at the interactive Simscape Result Explorer motor and drive block with all the analysis of simulation output. The next one, the control system overview. This is a state flow of the flight control. The helicopter needs to survive the cold Martian nights that can reach temperatures as low as minus 125 degree, so that the electronics and batteries cannot operate at such temperatures. So heater keeps the temperature in an acceptable range, so that the rotors consumes high amounts of power during flight, and the batteries can only provide such power above certain temperatures. So the heater must be used to reach such temperature before taking off. This is an important task. Nowadays these things are happen, so that the heater must be used to reach such temperature before taking off. The next one, the common dashboard subsystem. To control the helicopter interactively during the simulation, use the sliders, switches and knob blocks in the command dashboard subsystem. As the model solves the equations much faster than real time, the system enables simulation pacing to slow down the animation to the only 30 times faster than real time. Here the simulation result analysis with altimeter measurements. It shows the altimeter versus time and time versus temperature. The simulation plot shows altitude and battery cell temperatures using the interactive plot. The next one, the simulation plot of flight duration against the number of battery cells. This figure shows the altitude versus time and number of parallel strings of six cells with maximum flight durations. The total number of batteries directly influences the maximum possible duration of the light. We can add additional batteries to provide more energy storage, but this also increases the weight of the vehicle. Okay, these are Simscape result analysis. The Simscape result explorer with motor and drive block, what you discuss later. At the time now we are going to see with model. This is a Simulink model. It's a irradiance. We said this one. This irradiance blocks is a constant block. Initially the irradiance value make it as constant 0, and this is the solar panel. This solar panel block. This solar cell block models a solar cell, a parallel combination of current source, two exponential diodes and parallel resistors that are connected in series with the resistance Rs. The output current is given by this formula, this one, the solar cell formula, where Is and Is2 are the diode saturation currents, Vt is the thermal voltage, and N and N2 are the quality factors, and IPH is the solar generated current. Here itself in the cell characteristics we can set by parameterized by these 5 parameters we can choose for this design. The short circuit current, and these are all the values we are going to concentrate. Then panel configuration and temperature dependence value, energy gap. We should set the measurement temperature at 25 degrees Celsius, and the device simulation parameters at also 25 degrees Celsius. Then what is the solver configuration? The solver configuration blocks defines the solver settings to use for the simulation, and these are constant block also. It gives the output to the constant specified by constant value parameter. If constant value is a vector and interpret vector parameters as single dimension is on to treat the constant value as single array. This blocks is the current controlled temperature source. This current controlled temperature source block represent ideal energy source in the thermal network that can maintain a controlled temperature difference regardless of the heat flow rate. And we are discussed before the detailed battery pack. Here itself you can choose detailed battery pack, and also another option is simplified battery pack. How we can select with this simple one? Just you click hit here. Simply you can get this. You can see simplified battery pack and a detailed pack. If you select detail means it will select detailed battery pack. What is the difference between these two as battery pack variant? If you select for simplified battery pack can only see this. So one single cell solar pack, that is a battery pack, and the incident thermal mass block, and radiation to environment block, and SOC sensor value. It's a simplified battery pack. If when you go for another model, there is a detailed model. It has 6 batteries, 6 cell batteries. You can see now. Can you able to see? These are 6 cells. Cell 1, cell 2, cell 3, cell 4, cell 5, and cell 6. Here this heater is there, and next one is the same thing, insulated and thermal marks and the radiation to environment block. There are 6 cells as a 6 SOC sensors, and system set of charge sensors and temperature sensors are placed here to measure this number of trajectories versus temperature. Similarly, the heater is placed here. The heater subsystem block the resistor with thermal port. These block models are registered with optional tolerance, operational limits, faults and thermal noise modeling. To model the temperature effects, select the thermal variant here, thermal variant of this block by right click and selecting the Simscape block choices and show the thermal port here. This operating limits and faults, noise here where it is default value, you leave it. This is for heater. This is the next block is the important one, motor and drive block. In this motor and drive block represent a generic motor and a drive operating in torque control mode or equivalently current control mode. The block supports both motoring and generating regimes, and you can use it represent servo motor and traction applications at a system level. So that you can use this one. This one, the two gearbox for gearbox. This block represents an ideal non-planetary fixed gear ratio gearbox. The gearbox is characteristic by its only parameters called the gear ratio, which can be positive or negative. First one is a gearbox positive and next one gearbox negative. Connections on the S and O are mechanical rotational conserving ports associated with the box input and output shaft respectively. The gear ratio is determined as the ratio of input shaft angular velocity to that output shaft. This block generates torque in the positive direction if a positive torque is applied to the input shaft and the ratio is assigned to the positive value. Here also the source code is available here to set your gearbox sales nodes parameters value. Here ratio gearbox ratio you can choose, and variables and branches and what are the equations are there. Similarly, the rotors, two rotor blocks are there. This is it shows a simple rotor model. Represents a simplified helicopter rotor that converts rotary motion to vertical thrust. The thrust and rotor drag power are based on non-dimensional coefficients that are a function of vehicle advance speed ratio. The blade pitch angle is fixed here in this simple rotor block. The port R and C are mechanical rotational conserving ports associated with the shaft and casing respectively. The port V corresponds to the vertical translation motion conserving port. Here you can choose the direction of rotation of either positive or negative. For positive thrust you choose positive, for negative one you choose negative. And this is a propeller diameter, this is a tabulated value, and the advanced ratio vector and the interpolation method is smooth, if selected as smooth, and the exploration method is linear. Similarly for simple rotor for negative, you can see the one direction of the positive thrust is negative. Here this environment and advanced values, you click on rotational velocity at the shaft, and total mass block, this block represents an ideal mechanical translation mass. Similarly gravity, and this block creates a physical signal constant. This is for gravity input, then mechanical forces and sensors block. In this block the ideal translation motion sensors, and also this block, this ideal force, this block represent the ideal source for force that generate force proportional to the input physical signal. The same thing for a drag block. This block the represent also the mechanical translation viscous damper. It's a viscous damper. The connections R and C mechanical translation conserving ports, with R representing the damper rod, while C is associated with the damper case. The block positive direction is from the port R to C. It is a ground contact block. In this block represent a mechanical translation hard stop that restricts the motion of body between upper and lower bounds. The stop is implemented as a spring and damper that come into the contact with the slider at the bounds. The hard stop model can apply full stiffness and damping at the bounds of forces can be applied smoothly through a transition region. These are subsystem of these mechanical forces and sensors block. The next one, the flight controller block. These flight controller blocks, they includes the three PID controller blocks. The next one, system level controllers. This is a state flow of this flight control system to set the temperature, to the heating entry, and what is the when heater is off and fly is on, what is the land entry, what is the fly entry, also prepare for from fly entry. All the things are given in the form of state flow. Here these are interactive command dash prompt. In this dash prompt, the motion environment and flight command on and off option also there. You can give the attitude command in this way of up to 1 2 3. Here measurement and control states, it shows the battery, it shows the values of battery state of charge and battery temperature and attitude. You can increase the surface temperature by using this interactive dashboard operation. For see solar irradiance value you can set, and this one you can set the surface temperature. Now let us see the simulation. What will happen, you can see. And for example, also you can modify the model parameters by using this script file. You can store the parameters in the structure. This is Ingenuity parameters function is used to structure this Mars helicopter system level parameters. Is the environment, you can see the environment gravity and the environment density, mechanical Ingenuity value, and the total mass except batteries and propellers, motor and drives blocks and gearbox and battery, and main simulation analysis in the form of SOC and the temperature and the thermal parameters block and thermal model and initial conditions set, heater and solar cells. These are all the parameters you can change in this interactive Matlab script file. Here the total number of cells also you can increase, and also see the ISC values you can change, and VOC values, and IRS value, radiance current, also RS N series, N parallel, heater resistance and 40 ohms. Here itself for understanding purpose, for analysis purpose, you change the parameters value, see the result, and analyze with this option. Here for example, in this example, first you start with a detailed battery pack model, and also get plot attitude versus battery cell temperature. Now we can see attitude and battery temperature output. This one attitude and measurements for detailed battery pack, and then similarly the plot where flight duration versus number of batteries, because here we can in this detailed battery pack there are 6 cells are there, so that it takes 6 cells trajectories versus temperature, cell temperatures. Also by using the Simscape Result Explorer, you can see the motor drive subsystem outputs. It shows omega values and torque limit versus torque reference, power dissipated versus time. Also it describes the detailed battery pack, and what is the value of the cell 1, what is the Q value, charge value, you can see. Simulation is going on. Now we are getting the Mars helicopter system plot for the first for this is shows us charge. You can see the figure figure 2 and figure 3. Then next plot time duration versus time batteries are now showing. Also parallelly we can run this Simscape Result Explorer, so that it can not included the output for plots simulation result. Now it is showing. The graph shows the trajectories versus flight durations, flight duration versus number of batteries plot, flight duration versus number of you can also add this balancing of cells, 6 cells. You can use 8 cells or you can use 10 cells. Just you can see the plot for flight duration versus number of batteries. It's also possible. The next one, the same thing with this attitude plot. is also going with this output for finding. Now what is the time with this dashboard to see? You can see now parallel you can see. At the time of landing the heater is on. Now you can see now again I set the values. Okay, now you can see the again you run this model. I set the values are 25 minus 25 and the solar radiations are not showed here. Now you can see the heater is on. At the time of flying the green line is on, it is the peak value. Now flying, it is the peak values. The values are in attitude values are given for understanding purpose, for analysis purpose. Just you can increase the solar irradiation value and give the attitude command. What will happen you can see with this interactive flight command. Now I am adjusting with the 200 irradiance and the value is minus 75 and I am setting for value. Well, now what will happen you can see. Now I am running by interactive this dashboard functions. We can measure and control the state, and also giving by using the slider option you can give the surface vary the surface temperature and the solar radiation. Now heater is on with this low temperature. At the time of takeoff you can see, and the time of now flying what is the attitude value is 4. Okay, now you can see the outputs. This is for a detailed battery pack view model. Similarly you can choose it and analyze with a simplified model. In the simplified model you can use only this one pack. What will happen you can see. By using the dashboard function, the previous output, now you can see the outputs. Now it is coming. Battery cell temperature, for simplified model you can see now for the single battery you can see more number of attitude. This reaches 5. It's a simplified view. Similarly with the dashboard, compiling is going on. This helicopter statistics are shown. This also time flying, it shows this value. This is for a single battery, simplified single battery view. Okay, so I hope we are understanding the concept of NASA developed Mars helicopter system design, system level design with Matlab Simscape library for making this design with solar cell, solar panel, detailed battery pack, and heater model and motor drive, gearbox and rotor and mass values and system level controls and interactive command dashboard and flight control and scope systems, and also interactive result explorer. You can see, for example, how you can get this component. Just you click on I also given this model in my YouTube channel description box. Kindly utilize for educational purpose, not for any um, financial or any project consultancy purpose. Just okay, how we can get this component. For example, right click here, go to library link. In this library link, go to library link where it is taken, it is shows with the Simscape electrical library. It takes some more time for going to the library. Okay, where I can take this one triple E double E library. This is a passive. Here itself we can choose this one. Similarly, where I can take taken from the rotor is I'll go to the again right click library link, go to the library block. Here this one simple rotor block. It is the helicopter library, W helicopter rotor library. Similarly, gearbox. In this manner you can take this library block, subsystem block, each and every blocks. There are the subsystems or battery pack. In this battery pack also it is also taken from this library link. It shows because it's running, so that it is a hidden format. I hope we enjoyed this video for making a Mars helicopter system level design by NASA developed helicopter. Thanks for watching. If you are new viewer of my channel, means kindly subscribe my channel, and also give share and like and my videos, and also give worthy comments in my YouTube video channel. Thanks for watching. Thank you.